Okay, welcome back everybody. In this video, we're gonna move forward our discussion of dynamic models. Now, here I have a first order model, and below that, I have a second order model. And to be specific, in this video, we're gonna look at the formulation of transfer functions. So, for most people, this video is gonna serve as an introduction to the idea behind transfer functions. So I want you to think of transfer functions as nothing more than a way of mathematical communication. Okay, that's all. Like, there is no physical significance of a transfer function. It's just a way of communicating parameters of a dynamic behavior. Now, transfer function, the reason it's desirable is because it summarizes all the parameters, and these parameters may include the gain of the process, the time constant of the process, the damping factor, etc. The transfer functions are going to summarize all the parameters that characterize your dynamic system. And transfer functions can only be obtained in the Laplace frequency domain, and it is only possible to take transfer functions if your initial conditions, all of them, are equal to 0, aka it's necessary to have homogeneous initial conditions to obtain transfer functions. So the way this process the way the if I want to illustrate the process of obtaining transfer functions in the schematic, you first obtain your differential equation. Okay, the next step is to make sure that your differential equation is linear. So you're going to take your differential equation and you're going to linearize it. We're going to talk more about linearizing the differential equations. And once they've been linearized, you have to make sure that the initial conditions are homogeneous, aka equal to 0. In most cases, you'll notice that your initial conditions are not homogeneous, and we will look at ways of dealing with those situations in the upcoming videos. The next step is going to be the Laplace transform. Okay, which we have covered in previous videos. Now, once you've taken the Laplace transform, you have to solve the algebraic equation to obtain the form output over the input on the left hand side, and a polynomial, let's say a polynomial that is a function of s, on the right hand side. And this right here is going to be your final step where you obtain your transfer function. Okay, now let's apply this procedure for our first order model that we have here. So I'm just going to copy it below. Alright, so let's see. Alright, and obviously we need homogeneous initial conditions, so I'm gonna put x at t equals 0 equal to 0. Now this differential equation is already linearized and we have our homogeneous initial conditions, so we can just like move forward and take the Laplace transform of the left hand side and the right hand side. So once you do that, you'll be left with tau times s y of s plus y of s equals k times x of s. Notice how we don't have any information about the forcing function or the input. We don't know if the input is a step input. We don't know if the input is a sinusoidal input. So we're just going to take the general Laplace transform of the input slash forcing function. And once you rearrange this by factoring out y of s, you're left with tau s plus 1 on the left hand side and the gain of process times x of s on the right hand side. Finally, from here you can easily rearrange the equation by obtaining the fraction y of s divided by x of s and have your first order transfer function on the right hand side. So for a first order system, the transfer function consists of the gain of the process and the time constant of the process, which are the two parameters that characterize the dynamic behavior of a first order linear system. Now you can do the same for the second order model that I have here. And if you were following the mass spring system example from the Laplace transform video, you'll remember that for homogeneous initial conditions, for our homogeneous initial conditions that x at t equals 0 is 0 and at dx dt at t equals 0 being 0, the Laplace transform of this model gives the following result. You get s squared times tau squared y of s plus 2 eta tau times sy of s plus y of s equals k times x of s. Once again, a general Laplace transform of the forcing function, since we have no information how the input is going to behave. So once you rearrange this by factoring out y of s, and if I skip the steps for the algebra, you'll be left with the following expression: y of s over x of s on the left hand side and tau squared s squared plus 2 eta tau s plus 1 on the right hand side. And this is the transfer function for a second order linear model. And notice it's characterized by the gain of the process, the time constant of the process, and the damping factor. So the transfer function captures all the terms, all the parameters that will tell you how your dynamic model will behave. The gain captures how aggressive the process is, and the time constant captures how fast or slow the process is, and the damping factor is going to tell you how quickly the oscillations die down. Okay, so in this video we just looked at the method for obtaining the transfer functions, and in the next videos we're going to look at how Laplace transforms and transfer functions can be of extreme benefit and can make our lives very easy when we're dealing with multiple systems that are in series. Okay.